Welcome to Astro Odyssey. Explore the universe. Far beyond the familiar spiral arms of galaxies like the Milky Way, in a region of space where the night would appear almost perfectly black, there exists a structure so vast that it barely fits within the imagination of modern cosmology. It is not a cluster of galaxies, nor a cosmic filament stretching across the web of the universe. It is a single galaxy's radio structure. It's an enormous outpouring of energy and matter that stretches across 16 million light-years. Its name is Alcyoneus, and it is so large that it challenges the assumptions scientists have quietly carried for decades. Galaxies, we believed, could only grow so big. Gravity would eventually lose its grip. Energy would thin out. The cosmic environment would starve them. But Alcyoneus did not follow those rules. It kept growing. It kept expanding. And now it forces us to confront a deeper question. Is there a maximum possible size for a galaxy? Or have we just discovered that the universe has no ceiling at all? To understand the scale of Alcyoneus, you must first step outside the comforting boundaries of human perception. The Milky Way, our home galaxy, is already enormous. It spans about 100,000 light-years from edge to edge. That means a beam of light traveling at the fastest speed allowed by the laws of physics would take 100,000 years to cross it. Yet compared to Alcyoneus, the Milky Way is microscopic. You could line up 160 Milky Ways side by side. And only then would you begin to match the reach of Alcyoneus's radio lobes. If our galaxy were placed at the center of this giant, the outer edges of Alcyoneus would stretch far beyond anything we could ever see from Earth, extending into regions of space where entire galaxy clusters would fit comfortably inside its boundaries. But Alcyoneus is not a typical galaxy. At its heart sits a massive elliptical galaxy, relatively ordinary in size. What makes it extraordinary is the engine at its core. A supermassive black hole, devouring matter and launching twin jets of high-energy particles into the cosmos. These jets move at nearly the speed of light, carving tunnels through the intergalactic medium. Over millions of years, they inflate enormous radio lobes. Ghostly structures filled with energetic particles and magnetic fields. These lobes glow not in visible light, but in radio waves, invisible to the human eye. Only by using sensitive radio telescopes can we see the true extent of this cosmic giant. For decades, astronomers believed that radio galaxies had a natural size limit. The environment around them would eventually halt their expansion. The jets would lose energy. The surrounding gas would push back. The universe itself, expanding in all directions, would dilute the matter feeding the black hole. Everything pointed toward a ceiling, a maximum scale beyond which no galaxy's influence could reach. Yet Alcyoneus appears to brush against that ceiling. It is not just large. It is dangerously close to the theoretical limits predicted by our models. And that raises a troubling possibility. If something slightly larger exists, or if conditions were just right, could a galaxy grow beyond what physics currently predicts? To answer that question, scientists have begun exploring what some call the Alcyoneus Limit, the hypothetical maximum, size that a galaxy's radio structure can achieve before the laws of physics force it to stop. This limit is not written in a textbook. It is not a number carved into the equations of cosmology. Instead, it emerges from a complex balance of forces, each pushing and pulling against the others across millions of light years. Gravity pulls matter inward, feeding the black hole. The jets push energy outward, inflating the lobes. The intergalactic medium pushes back, resisting expansion. And the expansion of the universe itself slowly stretches everything apart. Imagine a balloon being inflated inside a thick fog. The balloon represents the radio lobes. The fog represents the intergalactic medium. At first, the balloon expands easily. The fog is thin, offering little resistance. But as the balloon grows larger, the pressure inside drops. The fog becomes more difficult to push aside. Eventually, the balloon reaches a point where it can no longer expand. The pressure inside is too weak, and the surrounding fog pushes back with equal force. The balloon has reached its limit. Now replace that balloon with a structure 16 million light-years across. Replace the fog with the sparse gas that fills the void between galaxies. Replace the air inside the balloon with streams of relativistic particles accelerated by a black hole. Suddenly, the analogy becomes far more complex. There is no simple pressure gauge. There is no fixed boundary. Instead, there is a delicate equilibrium between energy, gravity, and the expanding universe itself. This is where the existential question begins to emerge. If Alcyoneus is close to the maximum possible size, then the universe has a built-in limit to how large structures can grow. It means there is a point where gravity loses its authority, where matter becomes too thinly spread to hold anything together. Beyond that point lies entropy, the slow fading of structure into the dark. But if Alcyoneus is not the limit, if something larger is possible, then our understanding of cosmic architecture is incomplete. It would mean that under the right conditions, galaxies could grow to sizes we have never imagined, stretching across tens of millions of light-years like silent giants drifting through the void to explore this. Scientists have turned to simulations, not small, simplified models, but massive computational experiments designed to recreate the birth, growth, and eventual collapse of giant radio galaxies. These simulations track billions of particles, follow the flow of energy from the black hole, and measure how the jets interact with the surrounding environment. They allow researchers to push galaxies beyond the sizes we observe, testing what happens when the laws of physics are stretched to their limits. In these virtual universes, the experiment is simple. Build a galaxy like Alcyoneus, then keep feeding its black hole. Increase the jet power. Reduce the density of the surrounding gas. Stretch the cosmic environment. Then watch what happens as the radio lobes grow larger and larger. At first, the results are predictable. The lobes expand, carving out vast cavities in the intergalactic medium. They glow brightly in radio wavelengths. They grow from 1 million light-years to 3 million to 5 million. But as they approach the scale of Alcyoneus, something changes. The expansion slows. The jets begin to lose coherence. The particles inside the lobes spread out, becoming thinner and less energetic. The magnetic fields weaken. The structure becomes fragile, almost ghost-like. And then, at a certain scale, the expansion simply stops. Not because the black hole runs out of fuel, but because the universe itself refuses to support anything larger. This is the heart of the Alcyoneus limit. It is not a single force that stops growth, but the combined effect of many. The intergalactic medium becomes too thin to confine the lobes. The jets lose their pressure. The particles disperse into the cosmic background, and the expansion of the universe stretches everything apart faster than gravity can hold it together. If this limit is real, represents something profound. It means the universe has a maximum scale for coherent structures. Not just galaxies, but anything bound by gravity and energy. There is a size beyond which the cosmos itself becomes too empty, too stretched, too entropic to allow anything to remain intact. And yet, Alcyoneus sits right on the edge of that boundary. It is as if the universe allowed it to grow just far enough to reveal the limit, but no further. Like a cosmic warning sign. It marks the point where structure gives way to emptiness, but the simulations are not finished. Researchers continue to push the models further, testing more extreme conditions. What if the surrounding environment were even emptier? What if the black hole were more powerful? What if the galaxy existed earlier in the universe's history, when matter was more densely packed? Could something larger than Alcyoneus exist under those conditions? Some simulations suggest it might. Under very specific circumstances, radio galaxies could grow to 20 or even 30 million light-years across. But these scenarios are rare, requiring environments that are almost perfectly empty, and black holes that feed continuously for hundreds of millions of years. They are cosmic anomalies, unlikely to exist in the modern universe. Other simulations are less optimistic. They show that once structures reach around 5 megaparsecs, it's roughly 16 million light-years, the balance of forces becomes unstable. The lobes begin to dissipate. The jets fragment. The structure loses its identity, blending into the background of the cosmos. If those models are correct, then Alcyoneus is not just large. It is the largest structure of its kind that the universe will ever allow, and that raises a chilling thought. If the universe has a maximum size for galaxies, what does that say about its ultimate fate? As the expansion of space accelerates, driven by dark energy, structures will become more isolated. Galaxy clusters will drift apart. The intergalactic medium will grow thinner. The conditions that allowed giants like Alcyoneus to exist will disappear in the distant future. No galaxy will ever reach that size again. The cosmic environment will be too empty, too cold, too stretched. The era of giant radio galaxies will come to an end, leaving behind only smaller, quieter systems drifting in the dark. Alcyoneus, then, may not just represent a limit in size. It may represent a limit in time, a relic of an era when the universe was dense enough, energetic enough, and connected enough to support such colossal structures. And as we continue to simulate its growth, to push it beyond its limits, we are not just testing the boundaries of a single galaxy. We are testing the boundaries of the universe itself. At the center of every giant radio galaxy lies a paradox. The structure that stretches millions of light-years across the cosmos is powered by something smaller than our solar system. Hidden in the heart of the host galaxy, buried beneath layers of stars and gas, sits a supermassive black hole. It is a region of space so dense that not even light can escape its pull, yet somehow it becomes the engine that fuels the largest structures in the observable universe. To understand the Alcyoneus limit, we must first understand this engine, because everything about these colossal radio lobes begins with the behavior of matter at the edge of the event horizon. When gas, dust, and stars drift too close to a supermassive black hole, they do not fall straight in. Instead, they spiral around it, forming an accretion disk, a glowing whirlpool of matter moving at enormous speeds. As particles in the disk collide, they heat up to millions of degrees, releasing tremendous amounts of energy. Magnetic fields twist and coil through the disk like invisible ropes, storing energy that builds over time. And under the right conditions, that energy is released in the form of two narrow, powerful jets that erupt from the poles of the black hole. These jets are not made of ordinary matter moving at normal speeds. They are streams of charged particles accelerated to nearly the speed of light. Electrons, protons, and heavier particles are launched outward with energies so extreme that they can travel millions of light-years before slowing down. The jets slice through the surrounding galaxy, blasting past stars and gas clouds, eventually escaping into the vast emptiness between galaxies at first. The jets are narrow and focused, like laser beams cutting through space. But as they travel farther, they begin to interact with the intergalactic medium, the thin, nearly invisible gas that fills the space between galaxies. This gas is incredibly sparse, far thinner than the best vacuum ever created on Earth. Yet over millions of light-years, even this faint material becomes significant. It pushes back against the jets, slowing them down and causing their energy to spread out. When the jets finally lose enough momentum, they They inflate enormous bubbles of energetic particles and magnetic fields. These are the radio lobes, the structures that make galaxies like Alcyoneus so vast. They glow not in visible light, but in radio waves. Because the particles inside them spiral around magnetic field lines, emitting synchrotron radiation. This radiation can travel across the universe, eventually reaching radio telescopes on Earth, where it reveals the true scale of these giants. But the black hole alone does not determine how large the radio lobes will become. The galaxy itself, and the invisible scaffolding that holds it together, plays an equally important role. Every galaxy sits inside a massive halo of dark matter. It's an invisible form of matter that does not emit or absorb light, but exerts a powerful gravitational pull. These halos are not isolated. They are connected to one another by vast filaments of dark matter, forming the cosmic web that stretches across the universe. These filaments act like highways for gas. Over billions of years, streams of hydrogen and other elements flow along them, feeding galaxies and fueling star formation. They also provide the material that eventually falls into the central black hole, powering the jets that create radio lobes. In this way, the growth of a giant radio galaxy is not just a local process. It is connected to the large-scale structure of the universe itself. For a galaxy to produce something as enormous as Alcyoneus, it must sit in a very specific environment. It needs a powerful black hole capable of launching strong jets. It needs a steady supply of gas flowing in from dark matter filaments. And it needs a surrounding region that is relatively empty, so the radio lobes can expand without being crushed by dense intergalactic gas. This combination is rare. In dense galaxy clusters, the intergalactic medium is thick and turbulent. Jets struggle to push through it, and radio lobes remain relatively small. In extremely empty regions, on the other hand, galaxies may not receive enough gas to feed their black holes. The jets become weak, and the radio structures fade before they can grow large. Alcyoneus appears to occupy a cosmic sweet spot. It sits in a region of space that is neither too dense nor too empty. The surrounding medium is thin enough to allow the radio lobes to expand freely, yet the galaxy still receives enough material to keep the black hole active. For millions of years, the jets have continued to push outward, inflating the lobes to their enormous size. But this growth cannot continue forever. As the lobes expand, the energy inside them spreads out. The particles become more diffuse. The magnetic fields weaken. The pressure inside the lobes drops. At the same time, the intergalactic medium becomes increasingly difficult to displace, because the lobes must push against larger and larger volumes of space. This creates a kind of cosmic tug-of-war. On one side is the energy from the black hole pushing outward. On the other is the surrounding universe, resisting that expansion. At smaller scales, the black hole easily wins. The jets carve through space, inflating the lobes with little resistance. But as the structure grows, the balance begins to shift. To understand this balance, scientists look at the pressure inside the radio lobes compared to the pressure of the surrounding medium. As long as the lobe pressure is higher, the structure will continue to expand. But once the two pressures become equal, the expansion slows dramatically. If the external pressure becomes greater, the lobes may even begin to collapse or dissipate in simulations. This transition often occurs at scales similar to that of Alcyoneus, around 5 megaparsecs, roughly 16 million light-years. The pressure inside the lobes becomes too weak to sustain further growth. The jets can still inject energy, but it spreads out so quickly that it cannot maintain a coherent structure. The radio lobes become faint and diffuse, eventually blending into the background of the intergalactic medium. Another factor complicates the picture: the expansion of the universe itself. Space is not static. It is stretching, and that stretching accelerates over time due to dark energy. On small scales, gravity dominates, holding galaxies and clusters together. But on very large scales, expansion of the universe becomes more important. For a structure like Alcyoneus, which spans millions of light years, this expansion is not negligible. As the radio lobes grow larger, the space between their particles also expands. The energy inside them becomes diluted, making it harder for the structure to remain intact. In a sense, the universe itself is pulling the lobes apart. This introduces a fundamental limit. Even if the black hole continues to pump energy into the jets, there comes a point where the expansion of space outpaces the ability of the lobes to remain coherent. Beyond that scale, any additional energy simply dissipates into the expanding vacuum. This is one of the key ideas behind the Alcyoneus limit. It is not just about the power of the black hole or the density of the surrounding gas. It is about the interplay between gravity, energy, and the expansion of the universe. At some scale, these forces reach an equilibrium, and growth becomes impossible. Yet there is still uncertainty. The cosmic web is not uniform. Some regions are emptier than others. Some galaxies have more powerful black holes. Some environments may allow structures to grow larger than anything we have observed so far. That is why scientists continue to run simulations, testing different conditions and pushing the boundaries of what is physically possible in some scenarios. The jets remain stable for hundreds of millions of years, continuously feeding the lobes. The surrounding medium is extremely thin, offering almost no resistance. Under these conditions, the radio structure can grow far beyond the size of Alcyoneus, reaching scales of 20 or even 30 million light-years. But these simulations come with a caveat. As the structures grow larger, they become increasingly fragile. The jets begin to wobble. Instabilities form along their edges. Turbulence spreads through the lobes, breaking up the once coherent structure. The radio emission becomes patchy and faint. Eventually, the giant structure loses its identity, dissolving into the cosmic background, in other words. It may be possible to build something larger than Alcyoneus, but it would not remain a stable, recognizable structure for long. It would be more like a fading echo than a true galaxy-scale object. This raises a deeper question. What does it mean for a galaxy to have a size? Is it defined by its stars, its dark matter halo, or its radio lobes? If the radio structure becomes too diffuse to detect, does it still count as part of the galaxy? Or has it effectively disappeared even though its particles still exist? These questions are not just philosophical. They affect how we interpret the limits of cosmic structures. If we define size by detectable radio emission, then Alcyoneus may indeed represent the upper boundary. But if we consider the full extent of its influence, including faint, diffuse particles that are difficult to observe, the true size could be even larger. The more we study these giants, the more we realize that the universe does not provide simple answers. Instead, it offers boundaries that are soft and shifting, shaped by a complex interplay of forces. The Alcyoneus limit may not be a hard wall, but rather a threshold where structures become increasingly unstable and short-lived. And as we push our simulations further, increasing the power of the jets and lowering the density of the surrounding medium, we begin to approach that threshold. The structures grow larger than anything we have ever observed. They stretch across tens of millions of light years. For a moment, they appear stable. But then, slowly, almost imperceptibly, they begin to unravel. That is where the next phase of the simulation begins. In the early stages of the simulation, everything behaves exactly as theory predicts. The black hole at the center of the host galaxy feeds steadily, drawing in streams of gas from its surroundings. The accretion disk glows with immense heat, Its magnetic fields twist into tight spirals, and the twin jets erupt from the poles with relentless force. They move outward at nearly the speed of light, punching through the galaxy's outer halo and entering the vast intergalactic medium. At first, the expansion is effortless. The surrounding space is thin, almost empty, offering little resistance. The jets remain straight and focused like cosmic lances, depositing energy at their tips. Their shock fronts form, compressing the surrounding gas and inflating the radio lobes. The structure grows rapidly, reaching 1 million light-years across in what is on cosmic timescales, the blink of an eye. The simulation advances. 2 million light-years. 3 million. The radio lobes glow brightly, their magnetic fields strong and well-organized. The jets continue to supply energy, maintaining the pressure needed for expansion. Everything appears stable. By the time the structure reaches 5 million light-years, it begins to resemble the largest radio galaxies ever observed. The lobes are enormous, dwarfing the host galaxy at their center. The jets, though still powerful, now travel through regions of space that are more tenuous than anything encountered before. The intergalactic medium becomes thinner and colder, offering almost no resistance at first. This seems like an advantage. With less material pushing back, the lobes expand more easily. The structure stretches outward, reaching 10 million light-years. The simulation shows a giant nearly as large as Alcyoneus, glowing across the virtual universe. But then, subtle changes begin to appear. The jets, once perfectly straight, start to wobble. Tiny instabilities form along their edges, caused by turbulence in the surrounding medium. These instabilities grow over time like ripples spreading across the surface of a pond. The jets begin to twist slightly, no longer perfectly aligned with their original direction. Inside the radio lobes, the particles that once formed dense energetic clouds begin to spread out. The pressure drops. The magnetic fields weaken. The once bright glow of synchrotron radiation fades. It's becoming more diffuse. At 12 million light-years, the structure still appears intact, but the signs of strain are unmistakable. The jets are no longer smooth streams. They flicker, occasionally breaking into knots of energy that detach and drift into the lobes. The boundaries of the lobes become less defined, their edges fraying like the threads of an old fabric. By 14 million light-years, the simulation reveals a critical shift. The pressure inside the lobes has dropped to nearly the same level as the surrounding intergalactic medium. The balance that once drove expansion is now fragile. Every bit of energy injected by the jets spreads out across an enormous volume, becoming thinner and less effective. The structure continues to grow, but the expansion slows dramatically. Each additional light-year requires more energy than the last. The jets are still active, but they are fighting against a fundamental problem: dilution. The larger the structure becomes, the more its energy is spread out, and the weaker its internal pressure grows. At 16 million light-years, the simulation reaches the scale of Alcyoneus. For a brief moment, the structure appears stable. The radio lobes stretch across the virtual universe, enormous and majestic. The jets continue to feed them, maintaining a delicate balance. It is a cosmic equilibrium, a structure balanced on the edge of possibility. But the simulation does not stop there. The black hole continues to feed. The jets continue to push outward. The experiment is designed to answer a simple question. What happens if the galaxy tries to grow even larger? At 17 million light-years, the first signs of collapse appear. The jets, now traveling across unimaginable distances, begin to lose coherence. Turbulence grows stronger, disrupting the flow of particles. Instead of a steady stream, the jets break into clumps and eddies. Like a river turning into rapids, the energy they carry is no longer delivered efficiently to the edges of the lobes. Instead, it disperses along the way, heating the surrounding medium but failing to maintain the structure's integrity. Inside the lobes, the particles drift apart. The magnetic fields become tangled and weak. The once bright radio glow fades into a faint haze at 18 million light-years. The structure begins to unravel. The lobes lose their smooth, oval shapes. Their edges become irregular, torn by instabilities. Large pockets of low-pressure gas form, creating voids within the structure. The jets, now unstable, cannot compensate. They inject energy, but it dissipates too quickly. The simulation shows the once coherent giant fragmenting into diffuse clouds. It is still enormous, but it no longer behaves like a single structure. It is more like a collection of drifting remnants, slowly blending into the intergalactic medium. At 20 million light-years, the structure is effectively gone. The jets still exist, but they no longer inflate large, stable lobes. Instead, they produce faint, scattered patches of radio emission. The particles they carry disperse into the expanding universe. Losing their identity as part of a single galaxy-scale structure, the simulation continues for millions of years. The remnants of the once giant structure fade further, becoming indistinguishable from the cosmic background. Eventually, there is no trace left of the colossal radio galaxy that once stretched across the virtual universe. What remains is a quiet, almost empty region of space, with only a faint glow marking where the giant once existed. This moment, the point where the structure loses its coherence and dissolves into the cosmic background, is what defines the Alcyoneus limit. It is not a sharp boundary, but a threshold. Beyond this scale, structures cannot maintain their integrity. They become too diffuse, too fragile to spread out to survive. The simulation reveals a fundamental truth. There is a scale at which the universe itself becomes the dominant force. Gravity, energy, and magnetic fields can only hold structures together up to a certain size. Beyond that, the expansion of space and the thinness of the intergalactic medium take over. The giant does not explode. It does not collapse dramatically. Instead, it fades. It dissolves. It becomes part of the background of the universe. This is the ultimate fate of any structure that tries to grow beyond the cosmic limit. Not destruction, but dilution. Not collapse, but disappearance. And this has profound implications. If the Alcyoneus limit is real, it means the universe has a maximum scale for coherent structures. It means there is a point where growth becomes impossible, not because of a violent event, but because the universe simply becomes too empty and too vast. In the simulation, this moment is quiet. There is no explosion, no dramatic collapse. The giant simply loses its shape, its brightness, its identity. It becomes a faint echo of what it once was. But for scientists watching the data, this quiet moment is the most important of all. It marks the boundary between what the universe allows and what it forbids. And it raises a final, unsettling question. If Alcyoneus sits right at this boundary, if it is as large as a structure can possibly be, then we may be looking at the largest coherent galaxy the universe will ever produce, not just in space, but in time as well. Once the simulation shows the giant structure dissolving beyond the 16 million light-year scale, the natural instinct is to stop. The experiment appears complete. The limit has been found. The structure cannot grow any larger without losing its identity. But scientists rarely accept a single result as the final answer. The next question is inevitable, almost irresistible. What if the conditions were different? What if the surrounding universe were emptier? What if the black hole were more powerful? What if the structure formed earlier, when the cosmos itself was denser and more energetic. Could something larger than Alcyoneus exist under the right circumstances? Or is the limit absolute? To answer this, the simulation is reset. The environment is altered, the parameters adjusted. The goal is no longer to recreate a realistic galaxy, but to test the boundaries of physics itself. It is no longer a simulation of the known universe. It is a stress test of reality. In the first experiment, the density of the intergalactic medium is reduced. The virtual universe becomes emptier. The gas between galaxies thinned to an almost perfect vacuum. The black hole at the center of the host galaxy is given a steady, uninterrupted supply of fuel. Ensuring that the jets never weaken, the simulation begins again. The jets erupt, carving through space. The radio lobes inflate rapidly, facing almost no resistance from the surrounding medium. 1 million light-years. 3 million. 5 million. The expansion is smoother than before. There is less turbulence, fewer instabilities. At 10 million light-years, the structure is still stable. The lobes are large, but the internal pressure remains strong. The jets remain coherent, their energy delivered efficiently to the outer edges. At 16 million light-years, the scale of Alcyoneus is reached again. But this time, nothing begins to break. The structure remains stable. The lobes glow brightly. The jets are steady and straight. The simulation continues. 17 million light-years, 18, 19. For the first time, a structure larger than Alcyoneus appears stable, at 20 million light-years. The radio lobes stretch across the simulation like enormous wings. The host galaxy at the center is now almost irrelevant, a tiny speck compared to the vast structure surrounding it. The jets continue to pump energy into the lobes, maintaining their pressure. But as the simulation progresses, something subtle begins to change. The expansion slows. Not because of the surrounding medium, which is still extremely thin, but because of the expansion of the universe itself. The space inside the lobes is stretching. The particles drift farther apart. The magnetic fields weaken at 25 million light-years. The structure is still present, but its internal pressure has dropped significantly. The jets are now fighting not just against the intergalactic medium, but against the fabric of space itself. Every particle they inject into the lobes is immediately spread out by cosmic expansion. At 30 million light-years, the structure begins to show signs of instability. The lobes become patchy. The jets wobble. The energy is no longer sufficient to maintain a coherent structure across such vast distances. And then, slowly, the same process observed in the previous simulation begins to occur. The structure does not explode. It does not collapse inward. It simply fades, its energy diluted by the expansion of space. Even in an almost perfect vacuum, a giant cannot survive beyond a certain scale. The universe itself imposes a limit, but the experiment is not over in the next simulation. The focus shifts from the environment to the black hole. The central engine is made more powerful, not unrealistically so, but within the upper limits predicted by astrophysics. The black hole is given a mass tens of billions of times that of the sun, capable of launching jets far more energetic than those of typical radio galaxies. The simulation begins once more. The jets are brighter, stronger, and more focused than before. They carve through the surrounding medium with ease, inflating radio lobes at an astonishing rate. 5 million light-years are reached quickly. Then 10, then 15. At 20 million light-years, the structure remains stable. The powerful jets maintain high internal pressure, preventing the lobes from dissipating. The expansion continues. 20-5 million light-years. The structure still holds. 30 million light-years. The lobes are enormous, stretching across a region of space larger than many galaxy clusters. But even this immense power has its limits as the structure grows. The energy required to maintain pressure across its volume increases dramatically. The jets, though powerful, must now supply energy to a region of space so vast that their influence becomes diluted. At 35 million light-years, the pressure inside the lobes begins to drop. The jets are still active. Their energy spreads too thinly to maintain coherence. At 40 million light-years, the structure reaches its breaking point. The lobes fragment. The jets lose stability. The structure dissolves into diffuse clouds of particles, fading into the cosmic background. Even with an extraordinarily powerful black hole, the universe refuses to support a structure larger than a certain scale. But the most extreme simulation is yet to come. In the final experiment, scientists change not just the galaxy or its environment, but the era in which it exists. The simulation is rewound billions of years to a time when the universe was younger, denser, and more connected. Galaxies were closer together. The cosmic web was thicker. Gas flowed more freely along dark matter filaments. In this early universe, the conditions for growth are far more favorable. The simulation begins. The black hole feeds continuously, drawing in gas from dense filaments. The jets erupt, powerful and steady. The radio lobes inflate rapidly. 5 million light-years. 10 million. 15. The structure grows faster than in any previous simulation. At 20 million light-years, it remains stable at 25 million. It still holds at 30 million light-years. The lobes stretch across the young universe, glowing brightly. The dense environment provides enough material to sustain the jets, while the still moderate cosmic expansion allows the structure to remain coherent. For the first time, a giant larger than 30 million light-years appears stable. But this stability comes with a cost. The dense environment that feeds the black hole also begins to push back against the lobes. The intergalactic medium in the early universe is thicker and more turbulent. Shock waves form along the edges of the lobes. Instabilities grow. At 35 million light-years, the structure becomes unstable. Turbulence tears at the lobes, breaking them into irregular shapes. The jets struggle to maintain their direction. At 40 million light-years, the giant collapses into chaos. The structure fragments, its energy dispersed into the surrounding medium, even in the most favorable conditions imaginable. The universe imposes a ceiling across all simulations, regardless of environment. Black hole power or cosmic era. A pattern emerges. Structures larger than roughly 30 to 40 million light-years cannot remain stable for long. They either dissipate into the expanding vacuum or fragment under the pressure of their surroundings. This suggests that the universe has a fundamental upper bound for galaxy-scale structures. It is not a precise number, but a region of possibility, beyond which stability becomes impossible. And within that range sits Alcyoneus. At 16 million light-years, not at the absolute maximum, but close enough to be significant. It occupies a region where structures are still stable, but only just. It is like a skyscraper built at the edge of what engineering allows. Any taller, and the structure would sway, crack, and eventually collapse under its own weight. Alcyoneus may represent the practical limit of what the modern universe can produce. Larger structures may have existed in the past or under rare conditions, but they would be fragile, short-lived, and difficult to detect. This realization transforms the way we see Alcyoneus. It is no longer just a giant radio galaxy. It is a boundary marker, a signpost, indicating the edge of cosmic possibility, and it forces us to confront a deeper truth. The universe is not infinite in what it allows. There are limits not just to speed or energy or temperature, but to size itself. There is a scale beyond which structure cannot exist, where gravity loses its authority, and the expansion of space becomes the dominant force. Beyond that scale lies a different kind of universe, one without giants, one where matter is too thinly spread to form anything coherent, and that is where the final part of the story leads to the distant future, where the conditions that allowed Alcyoneus to exist will no longer be possible, and the universe itself will enforce the ultimate limit on all structures. If the simulations are correct, then Alcyoneus does not merely represent a large structure. It represents a boundary, a region of cosmic scale where the forces that build structure and the forces that destroy it reach a fragile equilibrium. It is a giant balanced at the edge of possibility, a structure that exists only because the universe, at this particular moment in its history, still allows such things to exist. But the universe is not static. It is not a stage on which galaxies grow forever. It is an evolving system driven by forces that change over billions and trillions of years. And among those forces, one stands above the rest in determining the ultimate fate of structure, the expansion of space itself. Ever since the universe was born in the Big Bang, space has been stretching. At first, gravity slowed that expansion. Galaxies pulled on one another, clusters formed, and the cosmic web took shape. For billions of years, gravity and expansion were locked in a cosmic tug-of-war. Then something unexpected happened. About 5 billion years ago, the expansion of the universe began to accelerate. Instead of slowing down, it started to speed up. Galaxies began drifting apart faster and faster. The space between them stretched at an ever-increasing rate. The cause of this acceleration is something we call dark energy. We do not know exactly what it is. It does not behave like normal matter or radiation. It does not clump into structures. Instead, it appears to be a property of space itself, an energy inherent to the vacuum that pushes everything apart. Dark energy now dominates the universe. It makes up nearly 70% of all cosmic energy, and its influence grows stronger over time. For structures like Alcyoneus, this has profound consequences. The radio lobes of giant galaxies depend on a delicate balance. The jets from the black hole inject energy, maintaining pressure inside the lobes. The surrounding medium provides just enough resistance to keep the structure coherent. But as dark energy drives the expansion of space, that balance begins to shift. The intergalactic medium becomes thinner. The cosmic web stretches. Gas flows along dark matter filaments become weaker. Galaxies become more isolated, drifting farther apart. Over billions of years, the conditions that allowed giants like Alcyoneus to exist begin to disappear. In the simulations, when the universe is allowed to evolve forward in time, the changes are subtle at first. Galaxies and clusters drift slightly farther apart. The density of the intergalactic medium drops. The gas-feeding supermassive black holes becomes less abundant. After tens of billions of years, the changes become dramatic. Galaxy clusters, once tightly bound, become isolated islands in a vast cosmic ocean. The space between them stretches so quickly that light from one cluster can no longer reach another. The observable universe shrinks, not because it is physically smaller, but because the expansion of space pushes distant galaxies beyond the horizon of visibility. Inside these isolated clusters, galaxies continue to evolve. They collide, merge, and form larger systems. But the supply of fresh gas from the cosmic web has been cut off. Star formation slows. Black holes run out of fuel. Without a steady supply of matter, the jets that once powered giant radio galaxies begin to fade. The structures they created dissipate into the background. In this far future universe, no new Alcyoneus-like giants can form. The conditions required for their growth, a balance between feeding filaments and a moderately dense intergalactic medium, no longer exist. The universe becomes a quieter place. Hundreds of billions of years pass. The last stars form and die. The largest galaxies settle into stable, slowly evolving systems. Black holes dominate the centers of these galaxies, but without gas to feed on, they become dormant. The era of giant radio galaxies ends. But the expansion of the universe does not stop. Trillions of years pass. The galaxies inside each cluster merge into a single, massive elliptical galaxy. The night sky, if anyone were there to see it, would be almost completely dark. There would be no distant galaxies visible, only the faint glow of the stars inside the local system. The cosmic web, once a vast network of filaments connecting galaxies across the universe, becomes invisible. Its structure remains, but the distances between its components grow so large that they can no longer influence one another. The universe becomes fragmented into isolated pockets of matter, each drifting alone through an ever-expanding void. In this era, the concept of a structure like Alcyoneus would be meaningless. There would be no environment capable of supporting something so vast. The intergalactic medium would be too thin. The supply of gas would be too small. The expansion of space would tear apart any structure that tried to grow beyond a modest size. The Alcyoneus limit, once a boundary discovered through simulation, becomes an absolute rule of the future universe. Not because of a specific law, but because the conditions required to approach that limit no longer exist. Time continues to move forward. Quadrillions of years pass. The last stars burn out. The universe enters what physicists call the degenerate era, a time when only the remnants of stars remain. White dwarfs, neutron stars, and black holes. Even these remnants do not last forever. Over unimaginable spans of time, they decay. White dwarfs cool into black dwarfs. Neutron stars slowly lose energy. Black holes, once thought eternal, begin to evaporate through a process known as Hawking radiation. The universe grows colder, darker, and emptier. Eventually, only black holes remain, drifting in the vast darkness. They are the last structures capable of holding matter together. But even they are not immune to the passage of time. Over timescales so vast that they defy comprehension, the black holes evaporate. One by one, they disappear, releasing their mass back into the universe as faint radiation. And then, at last, the universe reaches its final state. A thin, cold bath of particles and radiation spread almost perfectly evenly across an ever-expanding cosmos. No stars, no galaxies, no clusters, no filaments, no radio giants stretching across millions of light years. Only emptiness. In this final universe, the concept of size loses its meaning. There are no structures left to measure, no boundaries, no giants, no limits, because there is nothing left to be limited. And yet, billions of years earlier, there was Alcyoneus, a structure so large that it pushed against the edge of cosmic possibility, a giant that stretched across 16 million light years, balanced on the threshold between order and entropy. It existed during a brief window in cosmic history, when the universe was just dense enough, just energetic enough, and just connected enough to allow such things to form. It was not just a galaxy. It was a moment in time, a fleeting era when the universe permitted giants. The Alcyoneus limit is not just a boundary in space, it is a boundary in time. A marker of the era when structures could still grow to unimaginable scales before the expansion of the universe began to tear everything apart. In the end, the simulations reveal something both humbling and profound. The universe does allow giants, but only for a while. There is a maximum size for coherent structures, and there is a maximum era in which they can exist. Beyond those limits, gravity fades, energy disperses, and entropy takes over. Alcyoneus stands at the edge of that boundary, a silent, colossal reminder that even the largest structures in existence are temporary. And one day, in the distant future, the universe itself will grow too vast, too empty, and too cold to remember that such giants ever existed.